Schönen guten Morgen, willkommen.
Good morning and a cordial welcome to Ars Electronica 2011.
We have perfect English translation for all the conference. Please make sure that you have your headphones, and please let me use this moment already to say a very big thank you to our interpreters. They are really super experienced interpreters. They are working for us for more than 15 years already, so you can really be sure that you get the perfect translation in both languages, German and English. Die Ars Electronica heuer
Ars Electronica this year is entitled Origin, the way everything begins. And it takes us back to the origin of Ars Electronica. 32 years ago, in 1979, when Ars Electronica was organized for the first time in Linz, its title was already a festival for arts, technology, and society. The idea of bringing together artists and scientists to look at the changes in our world, to look at new technologies, how they influence culture, society, our view of the world. That is what Ars Electronica has been doing very consistently for 32 years. A great research center like CERN and cooperating with the top scientists of the world to plan and design a festival together with such scientists is not only fascinating in terms of science and fundamental research. More than that, we are convinced that fundamental research is one of the areas that creates free spaces, the free spaces we need for new ideas to be created, to emerge, and to be translated into practice. This is the very question the festival will take up, looking at natural sciences and looking at the arts to find out which measures, methods, and framework conditions need to be created in order to allow new ideas and new developments to emerge and to move forward. Ideally, this would have to happen not only within systems, but also on the basis of interdisciplinary and transdisciplinary cooperation, because this will stimulate society and its processes of thinking. When we look around in the world, be it Austria, be it the planet as a whole, innovations, particularly in the societal sphere, is the most important thing we need. As always, in Ars Electronica, we're going to have a number of conferences and specialized events. We have an extremely tight program. The main symposium is this one, taking place at Bruckner House. We have 5 sessions starting this morning with a presentation by one of the most highly qualified speakers on this subject, Paul Davies. He is going to talk about the Goldilocks Enigma and thus setting the stage for reflections in different directions of science. Then we're going to have a number of presentations dealing with CERN and its activities. Rolf Landur is going to give us an overview of how CERN emerged, what its mission is. He is the one at CERN responsible for the outreach program. You're going to see over and over again what an exemplary role CERN is playing in the communication of science. Sergio Bertolucci, the research director, is going to explain the LHC to us, and he will talk about the worldwide computer grid. Michael Doser is an expert in antimatters. And then we're going to have a live transmission from CERN. Fabiola Gianotti will be reporting from the LHC. I don't know if the protons can come across via Skype, but we do hope that we'll be able to communicate the great fascination this has to you. Anton Zeilinger and Johannes Kofler in the afternoon will focus on quantum physics. They will be taking us into a fascinating field. Lisa Randall is going to talk about physics and scale, and Derek de Kerkhove will take us back to the core issue of this conference, that is the implications these scientific findings have on our world view. Tomorrow morning, Umberto Maturana. We are extremely happy to have him here once again. He was here already in the 1990s. He's a brilliant speaker, over 80 years of age, and he's one of the profoundest thinkers when it comes to the convergence of art and science. Joichi Ito and Rolf Heuer will explore the question of how to manage centers of science, innovation, and cognition. We're then going to take up the central issue of what is art and science and cooperation between the two. I think there are so many misunderstandings, more misunderstandings than items on which we agree. But it's not only a question of identifying things we have in common, but also of identifying differences that separate us, even though we pursue the same goal. Tomorrow afternoon, for those of you who want to know all about CERN and what's happening there, can go to the Ars Electronica Center, to the deep space, to hear the presentation of a fantastic new book about CERN. And at the Ars Electronica Center, they can then listen to 4 scientists explaining the experiments. At the Bruckner House, in this room tomorrow afternoon, we're going to start our talks with the artists of the pre-Ars Electronica. For a number of years, we've had the hybrid art category, which is about the hybridization of art and science. We have Oron Katz here as a guest and a speaker. He was the winner of the first Golden Nika in this category. He's one of the people who profoundly explore this topic of how to build a functioning platform for cooperation between art and science, in which art is not just the water bearer to science, because science, with scientists saying that art has to explain what science is doing. No, it's much more than that, because scientists themselves need to explain what they are doing. And there is somebody who has written many books and articles on this subject. Paul Davies is here with us today.
Thank you for coming, and please come up to the stage. Thank you.
Ladies and gentlemen, good morning. And let me first apologize that I will be addressing you today in English and not in German. As I travel around the world and visit many countries, I'm always astonished at how good the English is that is spoken in all these countries. And yesterday when I checked into my hotel, I asked the young lady behind the desk do you speak English? And she said, of course. Well, I think we English people should not take it for granted that other people should learn our language. So I'd just like to start by thanking you for hearing me speaking in the English language. If I use any strange words that you don't understand, please raise your hand and I will try to explain. Now, Albert Einstein was fond of saying that the thing that most interested him in science was whether the good Lord had any choice in the nature of his creation. Now, this is probably a rather bad translation from the original German. And Einstein was not a conventionally religious person. He had what he called a cosmic religious feeling, but he often talked about God or the good Lord. And what he meant by this rather quaint statement is that he had puzzled for a long time about whether the world could be otherwise. This is a really big question. Could the universe be different? Does it have to be as it is? And if it does, if it could be different, if it doesn't have to be as it is, he would like to know, why is it the way it is? So these are very deep questions. These are questions that go beyond the normal scope of science. Scientists normally accept the laws of the universe and the world as we see it as given to us and go about exploring it. But theoretical physicists like Einstein often go beyond that and ask deeper questions about why the world is as it is and whether it could have been otherwise. Now, it seems very natural when exploring those deep questions of existence to think about the origin of things, the theme of the symposium here today. And although Einstein lived at a time when cosmology was not a well-developed subject, today it is. We know quite a lot about the origin of the universe. We know, for example, it began in a Big Bang about 13.7 billion years ago. So we can be quite precise about the date, 13.7 billion years ago. By comparison, our planet Earth and the solar system is 4.5 billion years old. So about a third as old as the universe. Now, how do we know that the universe began in a Big Bang? What is the evidence for this? Well, the initial evidence came many decades ago from the work of this man here. And I live these days in the United States, so I'm British and I also have Australian nationality, but I work in the United States, and it's quite common to tell lawyer jokes there. Lawyers are not much respected in the United States, and I usually say there that Edwin Hubble began on the dark side. He began life as a lawyer, but then he saw the light and became an astronomer. Hubble was interested in these objects here. We call them galaxies. And in those days, nobody quite knew what a galaxy was, whether it was a fuzzy cloud of gas within our own Milky Way, or whether it was like another Milky Way, another galaxy in its own right out there a much greater distance away. And what Hubble found was that the fainter the galaxies he looked at, the more red was their light. This is called the redshift. And he found this very easy to interpret. And I've got to give you a little demonstration. If you've ever had a flat tire on your car on the Autobahn and you pull over to the side, and it's a scary thing, you get out of the car and you jack the car up and you're taking the wheel off, and all the while the other vehicles are screaming towards you, and what you hear as they come is a sound something like this. I'm sure you're all familiar with it. I'll do that again. So that's called the Doppler effect, and it's because the sound of the approaching vehicle is squashed up as it comes towards you and stretched out as it goes away from you. Changes the frequency of the sound. Same thing happens with light. If something's rushing towards us, the light looks more blue, shorter wavelength, higher frequency. If it's rushing away from us, it looks red. So Hubble was able to say, these galaxies look red because they're rushing away from us. And because the more distant galaxies, the fainter ones, are even more red, this means they're moving away even faster. And the only way to understand this is that the entire universe is expanding. Maybe in question time people can ask me what that means. It doesn't mean all the bits and pieces are flying apart from a common center. It doesn't mean there was an explosion of a lump in a pre-existing void. What it means is that the space between the galaxies is swelling or stretching every day. So the galaxies aren't moving towards or away from anywhere. The whole thing is just getting larger and larger. Now, when Hubble first did these observations, he couldn't see very far out into the universe because he only had a small telescope. But today we have a telescope that's named after him, the Hubble Space Telescope. Here it is. And through this instrument, it's possible to see galaxies which are not just millions of light years away, but billions of light years away. In fact, the most distant galaxies currently being studied are about 12 billion light years away. Now, because when we see a galaxy a billion light years away, we don't see it as it is today. We see it as it was 1 billion years ago. So if we're looking 12 billion light years out into space, we're seeing the universe there as it was 12 billion years ago. And I've already told you it's only 13.7 billion years old. So we're looking back almost to the beginning of the universe. People should feel free to come and sit in the front row. I know they're always nervous about doing that, but I'm not dangerous, believe me. And this is a typical picture from the Hubble Space Telescope. And what you see there look like stars, but every dot on that picture, with the exception of that one there, every dot is a galaxy. And there are about 100 billion galaxies. So just to wrap your head around these numbers, our Milky Way galaxy contains about 400 billion stars, and there are about 100 billion galaxies within the range of the Hubble Space Telescope. Now, if the expansion of the universe was all there was to it, the only evidence for a Big Bang, you might be skeptical that such a thing really happened. But in the 1960s, a major piece of confirmation came from the work of these two rather sinister-looking characters. They looked like a couple of mafiosi. They worked at the Bell Telephone Labs in New Jersey in the United States. And this contraption here, this weird-looking antenna, there we are for the people there, weird-looking antenna, was an early attempt at satellite communication. And they found they were getting an annoying hiss from this instrument, and they got in the horn of the antenna and cleaned out the pigeons. They thought that might be doing it. But in the end, they concluded that this hiss was produced by microwaves coming from the sky. And we now know what that is. It's the heat radiation left over from the Big Bang. The Big Bang was not only very compressed with the whole universe. You imagine running the great cosmic movie backward to the beginning, everything would be very compressed, so very hot. And that heat radiation fills all of space. As the universe expanded, so it cooled down, and it now fills all of space at a temperature a little under 3 degrees above absolute zero, which is about minus 270 degrees centigrade. And that's like the entire universe being inside a microwave oven. So this is the afterglow of the origin of the universe. And if you look carefully at that radiation from a satellite, here's a picture from a satellite called WMAP, which stands for the Wilkinson Microwave Anisotropy Probe. You don't need to worry about these words. There's another one up there now with a more familiar name. It's called Planck. That's a European Space Agency instrument. And these instruments are mapping this heat radiation. That's a thermal map of the sky that you're looking at there. And the red bits are the hot bits, and the blue bits are slightly cooler. So slight variations in the temperature, not much, about 1 part in 100,000, but very, very significant. That's a real picture, not a simulation. That's what the sky looks like in microwaves. And in effect, that's a snapshot of what the universe was like 380,000 years after the beginning. Why 380,000 years? Well, that was the moment at which the universe became transparent to light. If you look at the sun, you don't see into the center of the sun, you see its surface. It's a luminous fog. Well, again, if you go back in the universe, there was a time when it was so hot, it was like the surface of the sun, a luminous fog. So we can't see back any further from that using light. So that's as far back as we can look, but that's still a long way back, 380,000 years after the beginning, compared to 13.7 billion years. Very substantial fraction of the age. And it's possible by studying the fine details, so scientists call it data mining, of all those little variations, to figure out how much matter there is in the universe, the age of the universe, and what its ultimate fate might be. Probably, anyway. Most of that information you can get from studying this heat radiation. I should say that these little variations on here are not just the creator making a pretty picture. These variations are crucial to our very existence because the hotter parts and the colder parts represent variations in the density of matter. And where there are more dense regions in the universe, so the gravity is greater and it pulls in material from the surroundings and gets even more dense. And eventually, over time, these dense regions grew into galaxies. So the seeds of the galaxies are present in that picture. If there were no variation, if it was exactly smooth, uniform temperature, smooth gas, there would be no galaxies. No galaxies, no stars, no planets, and no people, no observers like us to wonder of it all. Now, inevitably, we would like to ask, is it possible to know anything about the universe before 380,000 years? Can we go back to still earlier times? And the answer is yes, not so much by direct observation, but by exploring the physics that took place at earlier times. And the best way of exploring that physics, because as you go back in time, as the universe is younger and younger, so it's hotter and hotter, and the particles that were there were moving faster and faster with more energy, the best way of exploring it is to go to somewhere where they do high energy physics, that is, particle accelerators, where these subatomic particles, like electrons and protons, are accelerated to enormous energies and collided with each other. And that enables us in the lab to simulate the conditions that would have prevailed just after the origin of the universe. And I'm sure you already know that the best place to go for that is CERN, and the best machine to simulate the early universe is this one here. It's called the Large Hadron Collider. You're going to be hearing a lot about it today. It's an €8 billion project. It's up and running. It's working. Anybody who's been to CERN and has seen a particle accelerator, and in particular been to the control room and looked at the millions and millions of components must, like me, marvel at the fact that it works when they switch it on. In my home, probably about 20% of the time, the DVD player doesn't work, the television doesn't work, even the hot water system doesn't work. The fact you can have something with millions of components, switch it on, it works, I think is a fantastic tribute to the scientists and engineers involved. Now, from the sky, let me just go back. You see this is a curved tube. It's a ring-shaped tube called a torus. So it goes all the way around. It's 27 kilometers in circumference, that tunnel. And this is what it looks like from the sky. Of course, it's under the ground. But if it were on the surface, you'd see it would cross the frontier between France and Switzerland. And that's Geneva Airport there. And to give you some idea of the massive scale of this instrument, this is one of the detectors. So this, when this machine, I should say, the Large Hadron Collider, accelerates protons in counter-rotating beams to enormous energies, and then they smash together, and these machines are designed, detectors are designed to look for the debris that comes out, for reasons I'm not going to get into here. And look at this truck, the forklift truck. Gives you some idea of the scale of this. Now this instrument, when it reaches its full design specifications, will be able to simulate the conditions that prevailed in the Big Bang, not just 1 second after the beginning, not even a millisecond or a microsecond, but about a trillionth of a second. That's a millionth of a second after the Big Bang went bang. That's an astonishing thought, that we can directly recreate in the lab what the universe was like, just for an instant, what the universe was like a trillionth of a second after the beginning. I often like to make the comparison with the Bible that talks in terms of days, on the first day this, on the second day that. Well, science has moved well beyond talking in days. It can now talk about the origin of the universe, not on the first day, but the first trillionth of a second. But even that doesn't satisfy some people. They want to know, well, what happened before the first trillionth of a second? Indeed, what happened before the Big Bang? Did something actually cause it? And so this is a question that's been going around and around for as long as the Big Bang theory has been popular, for many decades. You see, it's even made it into a cartoon. For those who can't read this, it says, but before the big boing, what was there? And so everybody wants to know the answer to that question. Always comes up at dinner parties if I say I'm a cosmologist. Let me just run through a number of options to clarify this, because it's a very deep problem. In the past, people assumed that either the universe had been around forever or it was created at some particular moment in time. And so this is just depicted symbolically here. So we might imagine that for all eternity there was nothing. I'm going to show you there. All eternity there was nothing. And then at some particular moment C, the universe began. Boom, switched on. And so we've got before creation and after creation, and his time running like this. And this is the sort of picture I think most people have in their minds, even today, about the origin of the universe. That there was all eternity with nothing, and then a universe happened. But obviously this is a bit problematic, because we can always ask, well, what caused that event C? And there seem to be only two types of answers we could expect. One is a physical process made the Big Bang go bang, or made the universe begin. Even if there's no Big Bang, if the universe had a beginning, a physical process may have caused it. But then we would like to know, why did that physical process not happen before? If it was possible for it to happen, why did all eternity, why did an infinite amount of time elapse before the universe came into existence? So another type of explanation is some sort of God. Did God make the universe at some moment? Well, these both have problems, because, as I've said, if it's a physical process, why then? And then, if it was God, what was God doing before he created the universe? So this was a favorite taunt among pagans at the time that Christianity was becoming established in Europe and the Middle East about 1600 years ago. And the standard answer to the pagans to this question was busy making hell for the likes of you. But in the 5th century, a famous Christian theologian, St. Augustine of Hippo, came up with a neater answer to what was God doing before he created the universe. And Augustine said, quite explicitly, the world was made with time, not in time. It's a very important distinction. And here the picture shows the difference, because we still have a creation moment, but this is now at time equals 0. And this region down here that I've labeled nothing doesn't mean empty space sitting there for all eternity. It means no space, no time, no matter, no energy, no thing, nothing. And so this is a more profound view of creation, or the origin, I prefer to say, the origin of the universe. It's one in which time itself comes into existence with the beginning. So now we think of the Big Bang as the beginning of time. There was no time before the Big Bang in this picture. No time before the Big Bang. So the question, what caused the Big Bang, doesn't really mean anything if there was nothing there before it. It's very hard to imagine a time before time. Stephen Hawking has said it's like asking what lies north of the North Pole. It sounds like a sensible question. Saying what happened before the Big Bang sounds like a sensible question. But the answer to what lies north of the North Pole is nothing. Not because there's some mysterious land of nothingness there, but because there isn't such a place as north of the North Pole. It doesn't exist. It's not defined. And in the same way, in a simple picture of the Big Bang, there was no time before it. Before the Big Bang simply does not exist. Now, this raises its own set of problems, one of which is we would like to know whether the coming into being of the universe, even if it wasn't caused by something, nevertheless was something, a natural event, something that conforms with the laws of nature. But that raises a question about where did these laws of nature come from? The laws of physics that can permit a universe to pop into existence like that would seem to have some sort of transcendent existence. And the picture which many physicists carry around in their heads is a little bit like this, that the laws of physics are imprinted on the universe at the moment of its birth, a bit like the maker's mark. Boomf! Imprinted from without. The universe appears in a Big Bang together with a set of laws. Indeed, they think that the laws, in some sense, exist even if the universe doesn't, to permit the universe to come into being. But this raises a whole host of other questions. For example, we would like to know why, with Einstein, why are the laws of physics what they are? Could they be different? Might there be different laws? And if there could be a whole set of different laws, many, many laws, what we'd like to know is what is it that picks out the set of laws that apply to our universe, the laws of physics we know, like the laws of gravitation and electromagnetism and the laws governing particle physics, a whole set of mathematical laws. We would like to know why did they get singled out for the benefit of existence. Stephen Hawking has expressed this very poetically. He says, what is it that breathes fire into the equations and makes a universe for them to govern? We can have any number of equations, but these are equations that have a universe. Well, this leads us inevitably to wonder if the Big Bang was a natural event, and if there are laws that can bring the universe into existence without any supernatural act, it would be a very strange set of laws that happened only once, an event like the Big Bang just happening once. If it is the case, then, that the universe is a natural event, then you'd expect it to happen many times. If the Big Bang was a natural event, it must have happened more than once. And that leads to the idea that perhaps there are many Big Bangs scattered throughout space and time, each one giving rise to a universe, some like ours, some different, and the entire assemblage of all these universes is something that has become known as the multiverse. So when I was a student, it was fashionable to suppose, along with Stephen Hawking, that there's one universe with a beginning in a Big Bang and no time before it, and that was all. Today, the pendulum has swung, and it's fashionable to suppose that there are many universes forming a multiverse. And this assemblage of universes, this multiverse, has no beginning and no end. Each individual universe, like ours, begins with a Big Bang, and it has a history. It has a birth, an evolution, and maybe one day a death. But the totality of all these universes, the multiverse, has no beginning and no end. And this is the currently fashionable view. In another 20 or 30 years, it may be that there'll be some other view, but this is the one that people like at the moment. And one of the reasons they like it is because it explains one of the deep mysteries about the universe that's puzzled me through most of my career, and I call it the Goldilocks Enigma. Now, a few words are in order here, because talking about Goldilocks in the English language is something we all know. There's a fairy story, which I always assumed was a German fairy story, but I've had mixed fortunes as I travel around the world using the word Goldilocks as to whether anybody knows what I mean. And on one occasion I was talking in Bristol in the south of England at the Science Centre, and the director of the Science Centre there is French. It's a Frenchman, and he introduced me. I was talking about the Goldilocks Enigma, and he said, it's a pleasure to welcome the Professor Davies, but as for these Goldilocks, I know not. So, excuse my French. So he said he had no idea. In France, they don't know what Goldilocks is. So I'll just take you through the story quickly in case it's not part of Austrian fairy stories. So the story is that the young girl Goldilocks is walking in the forest, and she comes across a little cottage, and she's feeling very hungry and very sleepy, and she goes into the cottage, and it seems to be empty, but on the table are 3 bowls of porridge. If you know what porridge is. They eat it in Scotland. So she tries the porridge that belongs to Daddy Bear, and it's too hot. So she then tries the porridge belonging to Mummy Bear, and that's too cold. And then she tries Baby Bear's porridge, and that's just right. And she eats it all up and gets into bed and falls asleep. And the bears come back, and I don't know what happens. But she gets eaten, I can't remember. I'm sure it has a happy ending. But anyway, that's the story. And so when we talk about Goldilocks, we mean something that's just right. So the question is here, concerning our universe and its laws, that do seem to be just right for life to emerge, that is, for living organisms, including thinking beings like ourselves, that can come to exist. And let me just take you through this very briefly, because I want to allow some time for questions. Imagine that you didn't like the universe the way it is, and so you got hold of this device here. This is called a creation machine, and you can change things. And so one of these knobs, for example, if you twiddle the left-hand knob, you make all electrons in the universe a little bit heavier. And then you twiddle the next knob, and you make gravity a little bit stronger, and so on. You might wonder how many knobs there are in total that describe the physical universe to our best understanding. The answer is 30-something. 30-something knobs. Physicists call these undetermined parameters. Now, one day we may know why those numbers are the way they are, but at the moment, at our present state of knowledge, they're just arbitrary numbers. So you might wonder what would happen if you change some of those numbers. Would it make a big difference? And it turns out that some of those numbers twiddle some of these knobs by a tiny amount, and the universe would be dramatically different. So different that there could be no life. Now, we don't yet have the money to do the real experiment, I might say, but we can do the mathematical experiment. We can work out what the differences will be. I'm going to give you a couple of examples in a second, but Fred Hoyle, the great British cosmologist, I always like to give him a mention. He gave me my first job in Cambridge in 1970. He was very struck by these weird things. He said it's almost as if the universe is a put-up job. Now, it doesn't translate well into German, I'm sure. What he means is it looks contrived. It looks like it's a fix. Because these parameters I'm talking about, these numbers, like the mass of the electron, the strength of gravity, the strength of the nuclear forces, and so on. If you change them by even a little bit, this would throw everything out, and there could probably be no life. So let me give you an example, and it may be clearer. If you know any physics at all, you will probably know that the nuclei of atoms are made up of neutrons and protons, and I'm sure later on you're going to hear about the quarks that sit inside them, but let's just keep it simple, neutrons and protons. And the neutrons are just very slightly heavier than the protons, only about 0.1%, so hardly any difference, but it's absolutely crucial, because if something's heavier and it can transform into something lighter, it will do so. Nature always likes to go downhill, just like water likes to reach a bottom level. So on their own, neutrons will decay after about 15 minutes on average into protons. Now, if we imagine that the great cosmic designer had instead put it around the other way, that is, with the proton being slightly heavier than the neutron, just by a tiny amount, then instead protons would decay into neutrons. Now, that would be a disaster, because when the Big Bang coughed out protons and neutrons, the stuff of atoms, all the protons would have decayed after about 15 minutes into neutrons. And if there are no protons, there can be no nuclei of atoms, because the protons are the particles with electric charge that bind the electrons. So if there are no protons, there are no atoms. If there are no atoms, there's no chemistry. There's no chemistry, there's no biology. So just this little 0.1% this way, 0.1% that way, our very existence hinges on it. So that's one example. Here's another one, because I showed you this picture before. It's projected slightly differently. Those little hot and cold blobs, absolutely crucial. I mentioned that the density differences are about 1 part in 100,000. If they'd been 1 part in a million, okay, 10 times less, then that would be really bad news, because there wouldn't have been enough density of material to form galaxies. The universe would simply have expanded, and all the gas would have diluted, no galaxies. So no galaxies, no stars, no planets, no observers. On the other hand, if the density contrast have been 10 times greater, say 1 part in 10,000, the pull of the gravity of those dense regions would have been so great that it would have created monster black holes rather than galaxies. So either way, it looks like a rather delicate thing. If you turn one of those little knobs on the creation machine and got it out by a factor of 10 either way, again, it would be bad news for the universe. Now, the reason that the multiverse appeals to people is because it provides a natural explanation for why we live in a Goldilocks universe where all those knob settings are just right, all those numbers are just right for life. And this is an idea that is much championed by many of my distinguished colleagues, and in particular, Britain's Astronomer Royal, Martin Rees. I'll show his picture in a moment. So we have the idea then that there's a universe-generating mechanism that produces universes like ours and other universes, other Big Bangs, but that these universes come with different laws. So Martin Rees says that the laws of physics are just like local bylaws. So we used to think of the laws of physics as being like the laws of Austria handed down by the parliament in Vienna. That's it, same for everybody. But now it looks like the laws of physics are better thought of as like the laws of Linz. The local council makes the laws in the local area, and they don't necessarily apply in Vienna, Innsbruck. So if we think that the universe, each universe comes with its own set of laws, they're not really fundamental laws, they're more like local bylaws. And this is, happens to be a prediction of something called string theory. I'm not going to get into string theory, you're bound to have heard about it. I'll leave it to others to maybe take up that subject. I just want to make the point that whether it's string theory or something else, we can imagine that each universe comes with a distinctive set of laws. And now if these laws just assigned randomly to different universes, and maybe there's trillions and trillions and trillions of universes out there, each one with its own laws, then even if the laws are just random, here and there, just by chance, there will be a universe, a Goldilocks universe like ours, where the laws are just right for life. And so it's no surprise then that we see ourselves living in a universe that seems almost designed for habitation. It's almost as if there is a creator who has made the universe with all the right laws so that life can come to exist. But in the multiverse, the explanation is, of course, it's going to happen somewhere. We could not live in a universe that did not have laws suitable for life. So this is provided as an explanation for why the universe seems so well suited for life. And many people are satisfied with that. They say, well, that's okay. We've now explained this Goldilocks Enigma. We've now explained why the universe is just right for life. But I want to finish by leaving you with another thought. I'm not completely satisfied with this explanation. And one reason I'm not satisfied goes right to the heart of this thing we call science, which is so marvelous, and I've devoted my life to it. I'm a passionate scientist. For me, science is like a religion. I think it's a wonderful thing that human beings are able to uncover the laws of nature through scientific inquiry. And so one of the things that strikes me is that, of course, we will explain why the universe is just right for life by observing it. The observers will live in the bio-friendly universe, bio-friendly universes. Of course, that is the case. But we do more than just observe the universe. We've come to understand it. And this is the key point. We actually can do more than just look at the universe. By using science and mathematics, we've come to understand the universe and the subtle laws that govern it. Physicists like Albert Einstein, scientists of all persuasions, are able to dig beneath the surface reality that we see in daily life and uncover the deep, hidden mathematical order that makes the universe tick. And so this goes well beyond us being mere observers. We can also comprehend, we can understand the universe. And so there's a mystery still. And I'd like to leave you with this mystery in the words of the man who I quoted at the beginning, Albert Einstein. I suppose he's held up as the great exemplar of the magnificent scientist. And he expresses this sentiment, I think, very well when he says that the most incomprehensible thing about the universe is that it is comprehensible. So I think there is still something deep and meaningful and profound that connects human existence and human understanding with the existence of the universe, with its magnificent and elegant mathematical laws that underpin it. I think that's a great place to stop, and I'll take questions now. Thank you.